Today, first I'll start with second order condition. Last day, you got several exercises, and I hope at least some of you could try to find out the first order conditions. And I mentioned that today I'll mention once again about the second order condition, that is the bordered Hessian determinant. And then with those examples, you will complete both the first order and the second order conditions, and will be able to come to the proper conclusion whether the function is a maximum or a minimum. So could you check the first order conditions and solve several exercises, several examples? Kritika?
Yes, ma'am. The first two from the PPT that you sent, sorry, the slides, I could do them.
Oishani, Kunjuri?
Yes, ma'am, I could do it.
Yes, ma'am.
Okay. So let's start with the second order condition today. Already you got some idea, however, just with respect to the examples, etc., just to give some final impression. So in general, for the functions of n variables, the second order conditions in terms of bordered Hessian determinants can be presented as follows. If the Lagrangian function is like this, f of x1, x2 to xn. Last day, the example we did, and today also when we will go for the application part, we will go for utility maximization or expenditure minimization or output maximization or cost minimization. Whatever be the problems, we will stick to two variables under most of the circumstances. However, you are understanding when we are increasing the variable from 1 to 2, actually this is getting indication of more than one variables. So if there is n variables, the Lagrangian function will be written as f of x1, x2 to xn, where f is the original objective function. And we are adding the constraint part with the help of a Lagrange multiplier. So f of x1, x2 to xn plus lambda, where lambda is the Lagrange multiplier, into g of x1, x2 to xn. Actually, g of x1, x2 to xn equal to 0 is nothing but a constraint. So this is our new objective function, transformed objective function, where we bring together the original objective function and the constraint and create a new objective function. So if the Lagrange function f of x1, x2 to xn plus lambda g of x1, x2 to xn has a stationary value at x1 star up to xn star lambda star, then x1 star to xn star solves max the objective function subject to the constant if successive principal minors of h star alternate in sign in the following way. So L actually is equal to the Lagrange function. Capital L is equal to this expression. Okay, L is equal to this expression, this entire expression. So it will generate maximum if principal minors of determinant H alternate in sign in the following way. Okay. Now here the border has been added in this format. The border can be added in both the ways, first row, first column, or last row, last column. So both the ways you can add the border. Okay, borders can be added in both the ways, first row, first column, or last row, last column. Any way you can put the border. With H itself, therefore, taking the same sign as minus 1 to the power n. because you do not know at this moment what will be the value of n. Okay, so the final value will be -1 to the power n. Okay, if n is 2 or n is the even number, in that case you will, what will be the sign in that case if n is an even number? If n is even, what will be the sign of principal minor?
Positive.
Ma'am,
Positive.
positive.
Yes, very good. If n is even, then the principal minor will be positive. If n is odd, the principal minor will be negative. However, for maximization, we need this kind of sequence. For minimum, the same expression, if the objective function is to minimize this, all principal minors will be strictly negative. So in case of bordered Hessian or in case of constant optimization, when we are trying to get a maximum, in that case, principal minors will alter in sign starting with positive. And if we want to have, the minimum one, in that case, all principal minors will be strictly negative. All principal minors will be negative in case of minimization, alter in sign in case of maximization. So if we consider our two commodity world, the example we considered earlier, this example. If I consider this example, Z was f of xy, and the constant is given by g of xy is equal to c. And the Lagrangian expression is given by z is equal to f of xy plus lambda c minus g of xy. So if this is the particular function, in that case, we will be able to construct a matrix of order 3 by 3, a matrix of order 3 by 3 like this, and these matrix will be less than 0. The bordered Hessian determinant should be less than 0 if it is a minimum, and if it is a maximum, it will be positive. Actually, in case of maximum, it will alter in sign. If you have 3 commodity world, in that case, you will get the alteration. However, when you are at 2 commodity world, presentation of these particular Hessian determinant will indicate the second order condition, and presentation of this determinant is sufficient. So you can present only this determinant in presence of 2 commodity world. So when there are 2 variables, what we are finding that in case of minimum, the bordered Hessian will be negative. In case of maximum, the bordered Hessian will be positive. The easiest way to remember this thing, I hope everybody will work hard and try to understand why this is negative, why this is positive, etc. However, the easiest way to remember this thing, you are getting just the reverse sign of this second order, otherwise second order, which you get in case of maximum and minimum. When you did your mathematics at +2 level, for maximum, the second order condition will be less than 0. And for a minimum, the second order condition will be positive. Here just we are getting the opposite, For minimum, we are getting less than 0. For the maximum, we are getting greater than 0. So this is the easiest way to remember this thing. However, why it is less than 0, why it is greater than 0, there are mathematics behind it. So I hope everybody will grasp the idea of quasi-concavity, quasi-convexity, and try to understand how we are getting these signs. Okay, now the second thing, when we are deriving the second order condition, look here, what are the derivatives we are considering? When we considered unconstrained optimization, we considered, F11, F12, F21, and F22. Among these, F12 and F21 will be identical using the Young's theorem. Here also Young's theorem is applicable. Whenever you have Z lambda 1, that will be equal to Z1 lambda. Whenever you have Z lambda 2, that will be equal to Z2 lambda. and Z12 will be definitely equal to Z21. So all the Young's rule, etc., is applicable just like unconstrained optimization. However, apart from Z11, 12, 21, 22, three more varieties here we are considering: Z lambda lambda, Z lambda 1, and Z lambda 2. This Z lambda 1 will be equal to Z1 lambda, and Z lambda 2 will be equal to Z2 lambda. Okay. So to get the second order derivatives, what we need to do, we have to consider del square Z by del lambda square. Okay. And here, from this expression also you can find out del square Z by del lambda del X, del square Z by del lambda del Y. So three expressions we need to find out from this expression. Okay. And from this Zx, we will consider Zxx, and you can consider Zxy. Instead of calculating Z lambda x, you can also derive Zx lambda from this second equation. Okay, so del square Z by del X del lambda, that you can calculate from this equation, because that will be exactly equal to del square Z by del lambda del X. So it doesn't matter whether you are taking the derivative with respect to lambda first, then with respect to X, or with respect to X first and then with respect to lambda. From the third equation, you need to find out del square Z by del Y square, and along with that, you can find out del square Z by del Y del lambda. Okay, that will be similar to del square Z by del lambda del Y, which you are deriving from the first equation. So given these three equations, I'll request all of you to find out the derivatives. Please write down the value of Z lambda lambda. Whatever derivatives I'm telling you, please write down those expressions. So these three set of equations are there. That is, the first order conditions are with you. So please write down first these three equations, the first order conditions. The first order conditions. So this is your objective function, this is the constraint, this is the Lagrangian expression. Write down the first order equations. Once you write this first order equation, first order derivatives, derive all possible second order derivatives. That is, from here, find out Z lambda lambda. And tell me what will be the value of Z lambda lambda, or del square Z by del lambda square. What will be the value?
0.
0, yes. Because there is no lambda in the first order derivative. Once you take derivative with respect to lambda, you are getting back the constraint. So there is no lambda in it. So Z lambda lambda will be absolutely equal to 0. Okay, then you find out Z lambda x.
Minus gx.
Minus
gx.
Yes. Then Z lambda y.
Minus gy.
Yes. Next, Zxx. Del square Z by del X square. What is the value of Zxx?
Fxx minus lambda gxx.
Yes. And if you find Zx lambda, what is the value?
minus gx.
minus dx, so you are getting the same value. So we can apply the
Yes,
rules. When you are getting the first expression z lambda x, so there you can write equal to z x lambda. You got the value minus gx, that is equal to z x lambda by Young's rule. And find out the next one too. I'm coming in 1 minute. It's raining. Could you find out?
yes, ma'am.
Okay, so I hope you are understanding how you will find out the second derivatives. Given a numerical exercise, how we will find out the second derivatives. We'll put the value inside and check finally whether the determinant is negative or not, or whether the determinant is positive or not. Okay, so you will be able to come to the conclusion about your results. So this is another way to present the thing. So this z lambda 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 1 etc. that can be presented in this way too. Okay, can we present it in this way?
Yes, ma'am.
Okay. So so these are different ways of presentation. However, what you have to do given the objective function, so given these expressions, this example we discussed in the last class. So given these examples, now you need to check the second order conditions using the derivatives you derived just now. Okay, so you have to follow that mechanism. So would you please do the things, derive the second order derivatives for these particular numerical exercise, and tell me whether here x star y star is giving us the maximum or the minimum. This is a very typical expression, you know. ZXX is also 0, ZYY is also 0. This is a very typical numerical exercise. Most of the derivatives are equal to 0 here. So anyone who is who derived all the second order conditions, you know, would you please tell me what are the values? Z lambda lambda first.
0.
It's 0, 0.
Z lambda x.
Minus 1.
Z lambda y.
Minus 1.
Minus 1.
Minus. ZXX.
0.
0.
Z. And you know, just I'm not repeating, Zx lambda will be similar to Z lambda x. You are getting the same value. And ZYY.
0.
Okay. And ZXY.
1.
1.
To put these values in the second order expression, put these values.
Ma'am, it's coming positive, greater than 0.
It's coming positive. So if it is positive, then what will be your conclusion?
Maximum.
Maximum. Yeah.
Maximum.
Z is maximum at x star is equal to 3 and y star is equal to 3. Okay. Z is maximum at x star is equal to 3 and y star is equal to 3. In the similar way, you will be able to derive all the second order derivatives from exercise 2, and you will be able to understand whether Z, you know, is a maximum or a minimum. Is there anyone who has some problem in understanding how we are deriving the second order derivatives, how we are coming to the conclusion? Is there anyone? Do I need to repeat any part? Because now I'll move for the applications, you know, I'll move for the applications. So if you have any confusion, any clarification you need, so please ask me at this point. Okay, so I'll just request you to complete, you know, the second order part from all these exercises, you know. So we did the first order part. So please complete the second order part, as well as you consider these expressions. Okay, and check, first you consider the first order derivatives, derive the values, and then finally you consider the second order derivatives. Many a times you will need that. When you are trying to find out the border Hessian determinant, you need to plug the optimum values. Okay, the values you are getting from the first order conditions. So plug all those values there, plug all those values there. Okay, and check the sign of the derivative. So you complete all these things, and I hope you will understand. If there is any confusion with any numerical exercise, that we will discuss in the next class. So I think theoretical part is clear to all of you because nobody asked any question, and therefore I am shifting to the application part. Okay, so the first application I'll consider, that is the utility maximization exercise. We will maximize the utility function subject to the income constraint. That will be the thing. In case of utility function, we maximize u is equal to a function of x1, x2 subject to the budget constraint. Okay. M is equal to P1x1 plus P2x2, this kind of budget or income equation. So the constraint will be the income equation that we call the budget constraint. From the theoretical aspects which we covered in the first semester, you have idea about the constraint. Here, mathematically, how to resolve this thing, how to find out the point of tangency between the budget line and the indifference curve, only this part we need to learn. The theoretical concept is there, that there will be an income constraint and we will have a bunch of indifference curves, actually the entire indifference map. Among these indifference curves, the one which will touch the budget line will give the maximum. So we have the idea about this. The only task which is new, which we will learn, that is how to find out that point of tangency and how to ensure this is a utility maximizing solution. Okay. So consider the case of a consumer whose purchase is related to two commodities. Our ordinal utility function is given by u as a function of x1, x2, where x1 and x2 are the quantities of two commodities x1 and x2. The function f is continuous. It has the continuous first and second order partial derivatives. The function f is regular, strictly quasi-concave function satisfying the condition f11 f2 square minus f1 f2 f12 plus f22 f1 square less than 0. So all these things were revised. So what is the meaning of quasi-concavity? How we can express it when there are two variables in the analysis? So now you are informed about this. So directly we are using this expression. Partial derivatives of f are strictly positive. Here, the partial derivatives of f, that means f1, that is positive. f1 means del u by del x1. Del u by del x1 is the marginal utility of x1. Del u, f2 is nothing but del u by del x2. That is the marginal utility of x2. So from the nature of the utility function, the way we build up the utility theory, consumer behavior, etc., we consider all marginal utilities are positive. Only in case of bads, these marginal utilities will be negative. However, in case of goods, almost for all the commodities, in general, del u by del x is positive. So here we are assuming that f are strictly positive, implying that consumer will always desire more of both commodities. Okay, so here we are not incorporating the bads, pollution, etc. So here we are considering the goods, and marginal utility is assumed to be strictly positive. The equation of the indifference curve is presented by u naught is equal to f of x1, x2. Actually, when we have an utility function, we have u is equal to f of x1, x2. And when we plot a particular utility function with the help of an indifference curve, along a particular indifference curve, utility level remains constant. And therefore, the equation to the indifference curve is written as u naught is equal to f of x1, x2. Can you remember all these things? We did these things in the last class. How we present the indifference curve from the utility function. So we did this. Can you remember this? Yes or no?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So this is the equation to the indifference curve where u naught is a constant. Now, if we totally differentiate this equation, it becomes du naught is equal to f1 dx1 plus f2 dx2. Du naught is equal to 0 because along an indifference curve, the utility level remains constant. So du naught is equal to 0. So 0 is equal to f1 dx1 plus f2 dx2. And from there, we can derive the slope of the indifference curve. Okay. So the slope of the indifference curve, if I measure x2 along the vertical axis and x1 along the horizontal axis, the slope of the indifference curve is negative. You know, dx2 by dx1 is minus of f1 by f2. Both f1 and f2 are strictly positive, and therefore the indifference curve is negatively sloped. Now, if you take the second order derivative, d square x2 by dx1 square, you know, you will get this expression. If you consider the second order derivative, d square x2 by dx1 square, you will get this expression. Okay, so right hand side is there, f1 by f2. So please take this as homework. Derive d square x2 by dx1 square. Derive the second order condition, d square x2 by dx1 square, second derivative. And please check whether you are getting this expression is not. Okay, so this is your homework. Please note it down. Now, if we get this expression, you know, as f2 is positive, this f2 is positive, and by the definition of quasi-concavity, this is less than 0, the above expression is positive. Utility function is quasi-concave, as I mentioned in this slide. So if utility function is quasi-concave, you know, and if marginal utility is positive, in that case, this derivative is positive. The second order derivative is positive. Thus, the negative slope of indifference curve becomes larger algebraically and smaller in absolute value as x1 is substituted for x2. So along the curve, as we move towards a direction, the tangent becomes flatter and flatter. The tangent becomes flatter and flatter. So as the consumer moves along the IC, she requires more x1 and less x2, and the rate at which she is willing to sacrifice x2 to acquire more x1, that declines. Because you want to consume both the commodities. So if you continuously substitute one commodity by the other, you need more of the other commodity. So these things we discussed in the last micro session. So this is reflection of all these things. So you knew what will be the equation of the indifference curve. So we are using that. And you know how to derive the slope of the indifference curve. We are doing that. You have some idea about how to derive the curvature of the indifference curve. Here we are doing that. And more specifically, the conditions of quasi-concavity, etc., we are using, which we explicitly did not mention in the last semester micro class. Maybe in your mathematical economics class, you did this thing. However, in the micro class specifically, I didn't mention about quasi-concavity, etc. Any question? With these basic ideas about the utility function and the indifference curve, next we are trying to present how we will maximize utility subject to the income constant. A rational consumer will maximize utility subject to the income constant. M is equal to P1x1 plus P2x2. So combining the objective function and the constraint using the Lagrange multiplier, we can write the new objective function as z is equal to f of x1, x2. F of x1, x2 was our utility function. U is equal to f of x1, x2. So this is our objective function. So we are putting the objective function plus lambda, that is the Lagrange multiplier, then m minus p1x1 minus p2x2. That is the constant term minus p1x1 minus p2x2. So in this way, we are presenting the thing. However, if you want to present the expression as p1x1 plus p2x2 minus m, don't forget to consider the minus sign here. Both the things are right. If we write the variable part minus the constant, in that case, here the sign will be negative, And if I write constant minus P1 x1 minus P2 x2 is equal to 0 in this format, in that case, we have to consider the plus sign. So once we get the Lagrangian expression, we will take the first order derivatives. Z1 del Z by del X1. Del Z by del X1 will be F1 minus lambda P1. By first order condition, we are setting this to be equal to 0. So this is equation number 1. There is a typo. I don't know whether I'll be able to rectify it. I think I have tried in Word document. So I'll be not able to do it. It is Z2. Del Z by del X2, that is this will be Z2. Z2 is equal to, or del Z by del X2 is equal to F2 minus lambda P2. F2 minus lambda P2. That is equal to 0. This is equation number 2. And Z lambda, del Z by del lambda, we are getting back the constant itself. Whenever we will consider del Z by del lambda, always we will get back the constant. So M minus P1 x1 minus P2 x2 is equal to 0. So we are getting back the constant. Now we have to solve for two variables, x1 and x2. However, we have three equations. So as I mentioned last day, when we will go for application, you will find that we are combining equation 1 and 2. So what we will do from 1 and 2, if from 1 it is F1 is equal to lambda P1. From F2 it is, from equation number 2 it is F2 is equal to lambda P2. So I'm dividing equation 1 by equation 2 and getting this particular equation. F1 by F2 is equal to P1 by P2. This equation number 4. This equation is the equation to the income consumption curve, or ICC, or you can say broadly it is the equation to the angel curve. Okay, so what we will do, instead of finding the point of tangency between the indifference curve and the budget line, we will consider the ICC, income consumption curve, which is passing through the origin, which is a straight line, positively sloped straight line passing through the origin, and the point of tangency between the indifference curve and the budget line. So we will solve the budget line and this line. We will solve for the budget line and this line. Okay, so are you understanding, or I need to show the diagram? It will be a bit difficult for me to draw the diagram because I have to use the Word document. I do not have the board. So are you understanding better? Please
Can you repeat once?
Yeah, please draw the diagram in your copy. Please draw the diagram. Consider
Yes, ma'am.
two axes. Along the horizontal axis, consider x1. Along the vertical axis, consider x2. Then you consider a budget line. Consider an IC touching this budget line. Draw a straight line joining the origin and the point of tangency. Draw a positively sloped straight line joining the origin and the budget line, and you can extend this line a bit. For the indifference curve, mark it as U0. For the budget line, mark it as M is equal to P1x1 plus P2x2. The positively sloped straight line joining the point of tangency and the origin, mark it as ICC, income consumption curve. Could you complete this?
Yes, ma'am.
Beside ICC, when you wrote ICC, just beside that, within parenthesis, please add F1 by F2 is equal to P1 by P2. Okay, you marked the line as ICC within bracket, within first bracket, please write down F1 by F2 is equal to P1 by P2. Could do it? Everybody could do it?
Ma'am, but ICC is not always a straight line.
So you are drawing a straight line, positively sloped straight line. Okay. So what I am telling that instead of solving the problem as, deriving point of tangency between the indifference curve and the budget line, we can find out the same point solving two straight lines, the budget line and the equation to ICC. The two lines are intersecting each other at the point of tangency. Are you getting my point, everybody?
Yes, ma'am. Yes, ma'am.
Okay, so we are doing the exercise in that way. While we are using the Lagrangian expression and trying to solve the trying to find out the optimum amounts of x1 and x2, instead of finding the point of tangency, we are doing it algebraically. We are deriving the equation to the ICC, and that equation we are solving with the budget line and getting the values of x1 and x2. Okay, so once we get equation number 4, which is the equation to the ICC, that we are solving with equation 3 and finding x1 star, x2 star. These x1 star and x2 star will be the function of the parameters of the model. Now, what are the parameters of the model? Prices and income. So, it will be function of P1, P2 and M. P1, P2 and M. The demand for x1 and x2 derived in this way are ordinary or Marshallian demand. These are the ordinary or Marshallian demand. Okay, so this is the, based on total effect kind of thing. This is not based only on substitution effect or only on something else. So it is not that. It is not the compensated demand. The demand derived in this way is the ordinary or the Marshallian demand. It is not a compensated demand. Rather, it is the ordinary or Marshallian demand. Now, any question, anyone, for the graph part, for the equation part, how we are solving the exercise, any implication, any question for the utility maximization subject to income constraint? So far, we discussed only about the first order conditions. So everybody is understanding everything. Shampriti?
Yes, ma'am, I understood it. I'm just confused about one part. Lastly, when we are solving equation 3 and 4, how we are getting the values of x1 star and x2 star? Like, I did not get how we should solve it.
You did the diagram?
Yes, ma'am, I did the diagram.
Okay. So the two lines are intersecting at the point of tangency?
Yes, ma'am.
This is the way. So simultaneously solving the two equations, we will be able to generate the same amount.
Yes.
Drop perpendicular. from the point of tangency on x1 axis and x2 axis. What perpendicular?
Okay, ma'am. Okay, okay. I got it. Got it.
Okay, so you are getting x1 star and x2 star.
Yeah, ma'am. Thank you.
Okay. For rest of the students, everybody is understanding this?
Yes, ma'am.
Yes, ma'am.
Let's see. So once you get the first order conditions, derive the value, etc., you need to consider the second order derivatives to check whether this optimum value is giving you the maximum or the minimum. Okay, always you need to do this. So what you will do, you will consider z11 del square z by del x1 square, del square z by del x1 del lambda, del square z by del x1 del x2. So these derivatives, all these derivatives you may find out from equation 1. Then del square z by del x2 square, del square z by del lambda square, because rest of the derivatives you are deriving from the first order condition and you can apply Young's rule everywhere. So once you do these things, derive all possible second order derivatives, you have to plug the values here. You have to plug the values here. The second order condition. Z lambda, lambda, lambda 1, lambda 2, Z1 lambda, Z2 lambda, Z11, Z12, Z21, Z22. As you do so, you will find out a border 0 minus P1 minus P2. Now, if you look at this expression, if you consider del squared Z by del X1 del lambda, it will be minus P1. Or if you consider del squared Z by del X2 del lambda, it will be minus P2. So, you know, Z lambda 1 is minus P1, Z lambda 2 is minus P2. So if we put these values here, Z11, what about Z11? Z11 is simply F11. Z22 is simply F22. Z12 is F12, that is equal to F21, and which is again equal to Z21 by Young's rule. So we can put the matters here and we can write the expression as 0 minus P1 minus P2. And again, column wise also the same values will come and create the border. And we have F11, F12, F21 and F22. This is equivalent to this determinant can be presented as, you know, if you take the determinant, you know, it will give you these value F11, P2 square, etc. You know, so to have the positive expression for this, what you will find that this expression should be negative. Actually, you will get minus of this expression that is positive, which indicates this particular expression is negative. Okay, and that will prove basically the quasi-concave nature of the utility function. This expression will indicate the quasi-concave nature of the utility function. You will get just minus of this entire thing if you resolve this particular determinant. Would you please do it so that the thing will be clear? So after writing this expression, would you please take the determinant, would you please find out the value of this determinant? Would you please solve it and check whether you are getting minus of this expression? Are you doing this thing?
Yes, ma'am.
Yes, ma'am.
Once you get the value, please confirm whether you are getting minus of this entire.
Yes, ma'am, it's coming minus of this one.
Minus of this. Okay. So those who could complete that part, please substitute.
Yes, ma'am.
Okay, very good. And once you complete this thing, would you please substitute P1 is equal to F1 by lambda and P2 is equal to F2 by lambda in this expression? From where we are getting P1 is equal to F1 by lambda? You know, from this expression. From this expression. P1 is equal to F1 by lambda, P2 is equal to F2 by lambda. So would you please substitute P1 is equal to F1 by lambda and P2 is equal to F2 by lambda in this quasi-concavity expression, quasi-concavity type expression?
Yes, ma'am, done.
Done. Then you multiply the equation throughout by lambda square. It should be lambda square. It should not be the subscript. It will be superscript. Please multiply the equation by lambda square. Actually, we are doing it in both the sides. The right hand side is 0, therefore no reflection. So if you multiply this by lambda square, you are getting, I hope, the exact quasi-concave, the property of.
Yes, ma'am, this is a.
Okay. So the second order expression or second order condition is nothing but, you know, proving the quasi-concave nature of the function. Quasi-concave nature of the function when you are maximizing the function. It is indicating the quasi-concave nature. Actually, the quasi-concavity of the utility function is sufficient to have the second order condition. Okay. So sufficient to ensure that utility is maximized. Quasi-concave nature of the utility function is sufficient to ensure that utility has been maximized. Okay. So when you are doing all these things, you are deriving the second order condition, etc. The implicit thing in the entire analysis, entire second order analysis is the fact that if it is a maximum, need to check whether the basic function is quasi-concave in nature. If it is a minimum, we need to check whether the basic function is quasi-convex in nature. Okay, so this we are doing. This we are actually the idea behind the border decision determinant or checking the second order condition, you know, is that to ensure the utility function we considered is really quasi-concave in nature. If it is a minimization problem, we need to ensure the objective function we are considering that is quasi-convex in nature. Any question on the second order condition? What we are doing, what is its implication, how to find out the second order condition? Any question, anything? Very good, you are understanding, everybody is understanding everything. It's very, very good. Next, what I am doing, I'll try to interpret the Lagrange multiplier. Okay, so general interpretation we discussed in the last class. However, you will find that from context to context, the basic interpretation of lambda is varying a bit. Now, what is the general interpretation of lambda, which we discussed in the last class? Anyone, what is the general interpretation? I think we did it in the last class, isn't it?
Ma'am, it basically tells us the effect of the optimum value. If there's any small change in the constraint, that affect the value of the multiplier tells us.
Okay. So, however, that interpretation is coming in terms of optimum value function, isn't it?
Yes, ma'am.
So, and I also mentioned from context to context, the interpretation of lambda will vary a bit. Okay, so in context of utility maximization, let's see what is the interpretation of lambda. From the first two first order conditions, we can write lambda is equal to marginal utility divided by price. Okay, so if you look at the first order conditions, lambda is equal to F1 by P1. Lambda is equal to F2 by P2. So now lambda is marginal utility of the commodity divided by its price. Marginal utility divided by price. Okay. Since both F1 by P1 and F2 by P2 is equal to lambda, we can write F1 by P1 is equal to F2 by P2 is equal to lambda. The ratio of marginal utility and price gives the rate at which satisfaction would increase if an additional rupee is spent on a particular commodity. Okay, what is the meaning of mu by P? The meaning of mu by P is the rate at which the satisfaction would change if an additional rupee is spent on a particular commodity. Okay, if I spend one more unit on a particular commodity, what additional satisfaction we will get out of it? P is indicating the unit price. So if I spend 1 unit more, if I pay for 1 unit more, that means I am spending one additional money amount, the unit price of the commodity, to purchase one more unit. Okay, so this is the denominator. Numerator is the marginal utility. So it is it is showing that altogether, it is showing that how the satisfaction will change if I spend 1 unit more on a particular commodity. If more satisfaction could be gained by spending an additional amount on X1 rather than X2, the consumer would not be maximizing utility. If we find that, spending 1 unit more on X1, we are getting more satisfaction compared to the fact that spending 1 unit more on X2, in that case, you need to understand still you did not reach at equilibrium. At equilibrium, it is must that F1 by P1 should be equal to F2 by P2. Otherwise, consumer will continuously increase the consumption of the other commodity from where she is getting more satisfaction. By spending 1 unit more, if the person gets more satisfaction from X2, in that case, the person will substitute X1 by X2. Alternatively, by spending 1 unit more, if the consumer gets more satisfaction, in that case, the consumer will substitute X2 by X1. So we will be not able to find out the optimum solution, or we have to say we are yet to reach at optimum. Okay, so if more satisfaction could be gained by spending an additional amount on X1 rather than X2, the consumer would not be maximizing utility. She could increase her satisfaction by shifting some of her expenditure from X2 to X1, and hence at equilibrium, marginal utility divided by price must be equal for all commodities. In this line, the lambda can be interpreted as marginal utility of income or marginal utility of money. You will find that it is written marginal utility of income or marginal utility of money. Since marginal utilities of commodities are assumed to be positive, marginal utility of income or marginal utility of money is also positive. Here we are considering strictly positive marginal utilities. So marginal utility of money is considered to be positive. Okay. So if I consider lambda in this way, or if we get the value of lambda in this way, lambda can be finally interpreted as marginal utility of income or marginal utility of money. If I spend 1 unit more, what additional satisfaction I'll get out of it? If I spend 1 unit more on X1, what additional satisfaction we will get? If I spend 1 unit more on X2, what additional satisfaction we will get? So this can be interpreted as marginal utility of income or marginal utility of money. So lambda in case of utility maximization exercise can be interpreted in this way. Any question? Now we can extend this exercise for the n commodity world. Now if I have n commodity world, naturally the objective function, we will have quantities of all n commodities. Okay, so Q1, Q2 to Qn, quantities of all n commodities will come in the objective function. So the basic objective function will become f of a Q1, Q2 to Qn. Okay. The constraint or the income constraint or the budget constraint we can consider as y is equal to P1 Q1 plus P2 Q2 plus up to Pn Qn, or y is equal to summation I is equal to 1 to n Pi Qy. So that will be the constant. So if I consider the Lagrangian expression, or if we combine the objective function along with the constraint, the new objective function or the Lagrangian expression can be presented as V is equal to f of Q1 Q2 to Qn plus lambda into income minus expenditure. P1 Q1 plus P2 Q2 up to Pn Qn. This is nothing but expenditure. Okay. So income minus expenditure that we are putting here. Now, if there are n commodities, we will have n number of derivatives from that. That is del V by del Q1, del V by del Q2, del V by del Q3. And in this way, we will move up to del V by del Qn. So n number of first derivatives will be there. Along with that, the final first order derivative will be given by del V by del lambda. So we will have n plus 1 number of equations. In a 2 commodity world, we have 3 first order conditions. In n commodity world, we will have n plus 1 number of first order conditions. Okay, so equation 1 can be presented as minus of del Q by del Qi by del Qj is equal to Pj by Pi. So are you understanding this part? This is Fi minus lambda Pi is equal to 0. So if I take Fi means del F by del Qi. Okay, so if I consider two first order conditions, can we write the expression in this way? Any two first order conditions and divide 1 by 2. The way we got the ICC, F1 by F2 is equal to P1 by P2. This kind of thing. Actually, what I am considering, del Z by del X1 divided by del Z by del X2. This kind of thing we are considering. F1 by F2 is equal to P1 by P2. In the similar fashion, in n commodity world, we can consider these things. Del Qi by del Qj is equal to Pj by Pi. So please check whether you are understanding the matter or not. This indicates that the rate of commodity substitution will be equal to the relative price ratio. The rate of commodity substitution will be equal to the relative price ratio. Here, you will be not able to find out the ICC. Rather, you are reducing the number of equation by 1. Actually, you have to solve for n factors and you have n plus 1 equations. And for that matter, you need to adjust so that finally you solve n equations to find out n values. Okay. So one equation otherwise will become redundant. So you need to develop some meaningful mechanism by which you will be able to combine equations and you will be finally able to generate n number of equations. Solving n number of equations, you will get the optimum values of n commodities. That is the idea. In a two commodity world, we are combining the two first order conditions, generating ICC, and then solving the ICC with the budget line. This point of intersection between the ICC and the budget line is similar to the point of tangency between the budget line and the indifference curve. So we are deriving the same value using a different technique. Instead of using trigonometry, finding the point of tangency, we are doing it algebraically using the Lagrangian mechanism. So here also, you can reduce the number of equations considering minus del Qi by del Qj is equal to Pj by Pi expression, which is giving us MRS is equal to P1 by P2, that expression. And then we can consider these bordered Hessian determinants. So, for maximum, it will alter in sign starting with positive. So this will be the mechanism. In case of n commodity world, it will move like this. It will move like this. Okay, the border you can put here or you can put here. So you can consider 0 minus P1 minus P2 and 0 minus P1 minus P2 and write the equation in that format, or you can consider this in this way. So both the things are equally acceptable. So this is all about the utility maximization exercise, and now you have to solve for the numerical exercises. So everybody has Henderson and Quant, I think, because in the last semester we used Henderson and Quant. From Henderson and Quant, you solve for all utility maximizing exercise, utility maximization related problem. Complete all utility maximization exercises. Derive the first order condition, derive the second order condition, and check whether you are getting maximum at a particular combination of X and Y. So before coming to next class, that is Monday, you have some homework. First of all, I told you from F1 by F2, taking derivative of F1 by F2, check whether you are getting the expression which I have written in the slide, do it, and solve for exercises given in Henderson and Quant. Start with that. today some people have started Viva, etc. And therefore